Namaste. I am Mrs. Arumugalakshmi. Today we are going to discuss the problems in Lesson 2 Current Electricity of Class 12 Physics Matriculation. The first problem. The following graphs represent the current versus voltage and voltage versus current for 6 conductors A, B, C, D, E and F. Which conductor has the least resistance and maximum resistance? So here in x-axis they have taken the current and in y-axis they have taken the voltage. We have to calculate the resistance. We use our Ohm's law formula. V is equal to IR. So R will be equal to V by I. So in this graph, how to find resistance? We have to find the slope. Slope is given by y by x. Here y it is v and x is I. So if you find the slope of the curve, we will get an idea about the resistance. So for conductor A, the current value 4 ampere, that is the current value we have taken, and the corresponding voltage value. See the curve. For the value of I is equal to 4, the corresponding voltage value is 2 volt. So I is equal to 4 volt and V is equal to 2 volt. R is found using the formula R is equal to V by I. Substituting the V and I values, we get 2 by 4 is equal to 1 by 2, which is equal to 0.5 ohm. So for conductor A, the resistance is 0.5 ohm. Now we have to calculate for the conductor B. For the conductor B, the I value we have taken as 3 ampere. The corresponding V value is 4 volt. So R is equal to V by I. Substituting the value of V and I, we get 4 by 3, which is equal to 1.33 ohm. Similarly, for conductor C, I is equal to 2 ampere. The corresponding voltage is 5 volt. So R is equal to V by I, which is equal to 5 by 2, which is equal to 2.5 ohm. Next, for conductor D, I is equal to 2 ampere. The corresponding voltage is V is equal to 4 volt. So R is equal to V by I, which is equal to 4 by 2, which is equal to 2 ohm. From the graph itself, we can easily find. Similarly, for conductor E, I is equal to 4 ohm and V is equal to 3 ohm. So R is equal to V by I, which is equal to 3 by 4 is equal to 1.75 ohm. For the conductor F, I is equal to 2 ohm and V is equal to 2 volt. The resistance R is equal to V by I is equal to 2 by 5, which is equal to 0.4 ohm. So the corresponding values of resistance of the all 6 conductors have been found. The next problem, lightning is a very good example of a natural current. In typical lightning, there is 10 power 9 joule energy transfer across the potential difference of 5 into 10 power 7 volt during a time interval of 0.2 second. Using this information, you have to find the following quantities. First one, the total amount of charge transferred between the cloud and the ground. So total charge you have to find. Next, the total current you have to find. Next, the power delivered in 0.2 second we have to find. So first, let us write the given data. Energy is given as E is equal to 10 power 9 joules. The potential energy is given as 5 into 10 power 7 volts. The time interval T is equal to 0.2 second. First, we have to find the charge. We know the formula for current as I is equal to Q by T. From that formula, the expression for Q is equal to I into T. So we are using this formula to find the charge. So current in the lightning bolt is given by the formula I is equal to Q by T we know, and during that the energy, how much energy is released, the expression for energy is equal to power into time. So power is given by VI. So energy is equal to VI into T, whereas VI is the expression for power. We know that power is equal to the product of voltage into current. We have used this expression. So from this expression, you can find the value of I as I is equal to E divided by VT. E is the energy value which is given in the data, voltage is given, time is given. So substituting the values, you can find the current value. So the value found for current is 100 ampere. Now, from I value, using our formula Q is equal to IT, you can find the total charge transferred, which is equal to 100 into 0.2, which is equal to 20 coulomb. Next, the power delivered. Power is equal to, we know the formula V into I. V value is given 5 into 10 power 7 volt. I value also we have got now as 100 ampere. So multiplying, we will get the answer as 5 into 10 power 9 watt. This is the power. 10 power 9 is giga. So power is equal to 5 gigawatt. The next problem, a copper wire of 10 power minus 6 meter square area of cross section carries a current of 2 ampere. If the number of electrons per cubic meter is 8 into 10 power 28, calculate the current density and average drift velocity. This is again an easy problem. Area is given as 10 power minus 6 meter square. Current is given as 2 ampere. The number of electron is given as 8 into 10 power 28. Current density, we know the formula J is equal to I by A. Substituting the value of I and A, we get the answer as 2 divided by 10 power minus 6, which is equal to 2 into 10 power 6 ampere per meter square. This is the value of current density. Next, we have to find the average drift velocity. The expression for drift velocity is V suffix D is equal to I by NEA. So, substituting the number of electrons, E is the charge of the electron, A is the area, we get the formula as Vd is equal to 2 divided by 8 into 10 power 28 into 1.6 into 10 power minus 90 into 10 power minus 6. And finally, we get the answer as 1 divided by 64 into 10 power 3, which is equal to 0.15625 into 10 power minus 3, which is equal to 15.6 into 10 power minus 5 meter per second. The next problem. The resistance of nichrome wire at 20 degrees Celsius is 10 ohm. Its temperature coefficient of resistance is 0.004 per degree Celsius. Find the resistance at the boiling point of the water. We know the boiling point of water as 100 degrees Celsius. Our problem is to find the resistance at 100 degrees Celsius. So the given data are the resistance of nichrome wire at 0 degrees Celsius R0 is equal to 10 ohm. The temperature coefficient of resistance alpha value is 0.004 per degree Celsius. Resistance at boiling point of water RT we have to find. And we know the temperature of boiling point of water as T is equal to 100 degrees Celsius. Substituting these values in our formula for RT. RT is equal to R0 into 1 plus alpha into T minus T0, which is equal to 10 into 1 plus 0.004 into T minus T0. T is the boiling point and T0 is the reference temperature, which is given in the question as 20 degrees Celsius. So 100 minus 20, it is 80. 80 into 0.004 is again 0.32. So plus 1, it will be 1.32. Outside the bracket you have got 10. So 10 into 1.32, which is equal to 13.2 ohm. If you see the given data, the resistance at 20 degrees Celsius is 10 ohm. The resistance at 100 degrees Celsius is 13.2 ohm. So what we infer is, as the temperature increases, the resistance of the wire also increases. The next problem. The rod given in the below figure is made up of two different materials. Both have the square cross sections of 3 mm side. The resistivity of the first material is 4 into 10 power minus 3 ohm meter and it is 25 centimeter long, while the second material has a resistivity of 2 into 10 power minus 3 ohm meter and it is 70 centimeter long. What is the resistivity of the rod between its ends? So for the first material, the resistivity is given as ρ1 is equal to 4 into 10 power minus 3 ohm meter. The length is given, area of cross section, square cross section side, every data is given. So we will find the resistance of the rod R1 using the formula. R1 is equal to ρ1 L1 by A. Substituting the value, we get the answer as 111 ohm. This is for the first material. Now we will find for the second material. The resistivity of the second material is 5 into 10 power minus 3 ohm meter. Length is given. So substituting these values in the formula, R2 is equal to ρ2 L2 divided by A. Substituting the values, we will get the answer as 389 ohm. So the resistance between the ends of the rods. Here if you see the diagram, we understand that the two rods are connected in series. One at the end of one rod, the other rod is connected. So it is a connection like series. So here to find the total resistance in series, we will add the two resistance. So when you add here the two resistance, you will have 111 plus 389, which is equal to 500 ohm. This is the resistance across the ends. The next problem. Three identical lamps, each having a resistance R, are connected to the battery of EMF as shown in the below figure. Calculate the current in the circuit when S is opened and closed. So when S is open, you have got the current passing through the three bulbs. So the three bulbs will glow. Whereas when S is closed, you have the current passing through the first two bulbs only. So the first two bulbs will glow and the C will not glow. So we have to find the current. Next we have to find what happens to the intensity of the bulb A, B and C. We have to calculate the voltage across the three bulbs when S is opened and closed. Calculate the power delivered to the circuit when the S is stopped and closed. Does the power delivered to the circuit decreases, increases or remain the same? We have to find. So the resistance of the ideal lamp. So for one lamp we will take the resistance as R. The EMF of the battery is taken as psi. According to Ohm's law, psi is equal to IR. That is V is equal to IR. EMF is nothing but the voltage. So first let us find the current. So when the switch is open, we will find the current in the circuit. First, before finding the current, we will find what is the total resistance. The total resistance is the three resistances are connected in series. So the total resistance formula, we use the series formula as Rs is equal to R1 plus R2 plus R3. Here the three values of resistance are equal. That is R1 is equal to R2 is equal to R3 is equal to R. So the total effective resistance Rs is R plus R which is equal to 3R. So current will be I is equal to V by R, that is epsilon, which is the EMF, divided by Rs. Rs value is 3R. So substituting, we will get the answer as I is equal to epsilon by 3R. This is I when the switch is open. So I suffix O is equal to epsilon by 3R. Next, the switch is closed. When switch is closed, we will find the current in the circuit. So first let us find the resistance. When the switch is closed, the total resistance will be only two bulbs will be. The current will be passing through the two bulbs. So the resistance is R plus R, which is equal to 2R. The current expression is I is equal to epsilon by Rs. Rs value is 2R. Hence, the current of the closed circuit IC is equal to epsilon by 2R when the switch is closed. IC refers to the current when the switch is closed, which is equal to epsilon by 2R. The intensity, when the switch is open, all the bulbs glow with equal intensity because the same current is flowing. In a series circuit, we know that the charge, the same current will be flowing throughout the circuit. When the switch is closed, the intensity of the bulb A and B equally increase. Bulb C will not glow since no current passed through it. The current will pass through the first circuit only, not through the second one. So the bulb C, which is connected in the next part of the circuit, will not glow. Next, we will find the voltage across the three bulbs. First, when the switch is open, voltage is given by the formula VA is equal to Ohm's law I into R. Here I naught in the sense I0 is the current when the switch is open. That we have already found as epsilon by 3R, and the resistance is R, so into R, so RR will get cancelled. So when the switch is open, the voltage is epsilon by 3. Similarly, the voltage across B and C will also be epsilon by 3 and epsilon by 3. When the switch is closed, IC value we have found that epsilon by 2R. So voltage across the bulb A is equal to VA is equal to IC into R is equal to epsilon by 2R into R. Again R and R get cancelled and we will have the value as epsilon by 2. Similarly, if we find the voltage across B and C, you will get voltage across B is equal to IC into R, which is equal to epsilon by 2, and voltage across C will be equal to 0 because no current flows through the C. So the voltage across the bulb C also will be 0. Next, the power delivered to the circuit. We know the expression of power as P is equal to V into I. The voltage value, current value when the switch is open. Just now we have found. So substituting those values we get PA is equal to epsilon by 3 into epsilon by 3R, which is equal to epsilon square by 9R. Similarly, the value of power across the bulb B and across the bulb C will be the same, which is equal to epsilon by 9R. Similarly, when the switch is closed, the power is given by V into I, which is equal to epsilon by 2 into epsilon by 2R, which is equal to epsilon square divided by 4R. Similarly, the power across the bulb B will be epsilon square by 4R, and for power across the C will be equal to 0 because no current flows and no voltage difference across the C when the switch is open. The total power delivered to the circuit will increase. From the expression of power, we can find that the total power delivered to the circuit increases. The next problem, the current through an element is shown in the figure. The figure is a plot between time and current. Time is taken in x-axis and current is taken in y-axis. Determine the total charge that passes through the element at t is equal to 0 second, t is equal to 2 second and t is equal to 5 second. This is again an easy formula. Easy problem. We use the formula I is equal to dq by dt, so from this we have to find the expression for dq. So dq will be equal to I into dt. So we have to just multiply the I and time value. We will get the total charge. So first one, at t is equal to 0. At t is equal to 0, if you see the graph, at t is equal to 0 second, the value of current is 10 ampere. So the total charge is I into dt. That is, I value is 10 ampere, dt is 0. So 0 into 10 it is 0 coulomb. At t is equal to 2. At t is equal to 2 second, if you see the graph, the value of I is equal to 5 ampere. So dq is equal to I into dt is equal to 5 into 2, which is equal to 10 coulomb. Similarly, at t is equal to 5, the value of current is equal to 0. So the value of charge is I into dt, which is equal to 0 into 5, which is again equal to 0 coulomb. The next problem. An electronics hobbyist is building a radio which requires 150 ohm in her circuit, but she has only 220 ohm resistor, 279 ohm resistor and 92 resistors are only available in her home. How can she connect the available resistors to get the desired value of resistance? So you have given 3 resistors. So you have to check when you connect these 3 resistors in series or parallel, 2 in series, 1 in parallel, 2 in parallel, 1 in series. So you have to do the combination and the effective value, final value, you have to get it as 150 ohm. So first here what we are trying is, first we try the parallel combination of R1 and R2. So for this parallel combination, we know the effective resistance value as 1 by Rp is equal to 1 by R1 plus 1 by R2. Substituting the value, taking LCM and multiplying, you get the value as 58 ohm. Now this connection is connected to the third resistance R3 as series. That is R1 and R2 are connected in parallel. To that parallel combination, we are connecting R3. The diagram is given side. Just refer. R1 and R2 are connected in parallel. To this parallel combination, we are connecting a resistor R3. So now using the series formula, the effective resistance was found as 58 for parallel combination. Now this 58 is connected with R2 in series. So the effective resistance is Rp plus R3 using the series resistance formula. So 58 plus 92 is 150 ohm. So the above connection will be used to get the value of 150 ohm. Next problem. A cell supplies a current of 0.9 ampere through 2 ohm resistor and a current of 0.3 ampere through a 7 ohm resistor. Calculate the internal resistance of the cell. So first I1 is given as 0.9 ampere. The resistance is given as 2 ohm. Current from the cell I2 is given as 0.3 ampere and the resistor is given as 7 ohm. We have to find the internal resistance of the cell small r. We know the formula for current in the circuit as I1 is equal to V by R, which is our Ohm's law. Instead of R, we have to substitute the combination of internal resistance and the given resistance. So it will be R plus R1. So from this equation, you find an expression for epsilon. So epsilon will be I1 into R plus R1. So current in the circuit, similarly for the second circuit, the current is given as 0.3 ampere. So I2 is equal to epsilon by R plus R2. So here also once again if you find an expression for epsilon, it will be I2 into R plus R2. Both the cases in equation 1 and 2, the LHS is the same, the EMF. So we can equate the RHS. So if you equate the RHS, you get the equation as I1R plus I1R1 is equal to I2R2 plus I2R. So now we rearrange this equation such that small r is on LHS and the remaining terms are in the RHS. Now we will find the expression for R as I2R2 minus I1R1 divided by I1 minus I2. Substituting the values of I1, I2, R1, R2, we get the value as 0.3 divided by 0.6, which is nothing but 0.5 ohm. The internal resistance value is 0.5 ohm. The next problem. Calculate the current in the following circuit. We have to find the value of I1 and I2. So if you take this circuit, first we are taking the junction B. In junction B, we apply our Kirchhoff's first law. So when you apply I1 minus I2 minus I3 is equal to 0 because I2 and I3 are moving away from the junction. So we give a negative sign. So you can take all the negative terms to the RHS. So we get the equation as I1 is equal to I2 plus I3. This you keep it as equation 1. Now take the loop A, B, E, F, A. That is the first loop. So in the first loop, we have to apply the Kirchhoff's second law. So when you substitute 100 I3, start from B. So it will be 100 I3 plus 100 I1 will be equal to the voltage in that loop. The voltage in the loop is 15 volt. So this value is equal to 15. Now substitute for I1 we have to substitute the equation 1 which is I2 plus I3. So when you substitute this value we get 100 I3 plus 100 into I2 plus I3 is equal to 15. Taking this 100 inside the bracket and simplifying we get 200 I3 plus 100 I2 is equal to 15. Keep this equation as 2. Now take the second loop which is B, C, D, E, B. So in the second loop again apply Kirchhoff's second law. We get 100 I2 minus 100 I3 because I3 is flowing in the opposite direction to I2. So we give a minus sign which is equal to minus 9 volt. The current in 9 volt is again in the opposite direction. So we have a minus sign. So now rearranging the terms we get 100 I3 minus 100 I2 is equal to 9. Now have this equation as 3. Now we have to add equation 2 and 3. When you add equation 2 and 3 we get 200 I3 plus 100 I2 is equal to 15. 100 I3 minus 100 I2 is equal to 9. These two equations when we add plus 100 I2 minus 100 I2 will get cancelled and we will have 300 I3 is equal to 24. So when 300 I3 is equal to 24, I3 will be equal to 24 by 300 which is nothing but I3 is equal to 0.08 ampere. Now this value of I3 we have to substitute in equation 3. So when you substitute we will get 100 into 0.08 minus 100 I2 is equal to 9. Further simplifying, following my steps, when you simplify you will get the answer of I2 as minus 0.01 ampere. Now substitute the value of I2, I3 in equation 1 and when you simplify you will get the value of I1 as 0.07 ampere. So we have found the value of I1, I2 and I3 by applying Kirchhoff's first law and second law, and just like solving algebraic equations we found the value of I1, I2 and I3. The next problem. A potentiometer wire has a length of 4 meter and a resistance of 20 ohm. It is connected in series with the resistance of 2980 ohm and a cell of EMF 4 volt. Calculate the potential along the wire. So length of the wire is given as 4 meter, resistance is given as 20 ohm. The resistance when it is connected with series with the potentiometer wire is given as 2980 ohm and the EMF of the cell is 4 volt. The effective resistance, since they are connected in series, the effective resistance will be 20 plus 2980 which is equal to 3000 ohm. You can find the expression for current using our Ohm's law. I is equal to V by R. Substituting the value we will have it as 4004 divided by 3000. The potential drop across the wire V is equal to IR. So I value it is 1.33 into 10 power minus 3 into R value, if you substitute 20, you will have potential drop as 26.6 into 10 power minus 3 volt. Here they have asked you to find the potential gradient. Potential gradient means potential drop across the wire across the given length of the wire, that is V, the total potential divided by the length. So substituting the total potential value, which is 26.6 into 10 power minus 3 divided by 4, we get the potential gradient as 0.66 into 10 power minus 2 volt per meter. Next, determine the current flowing through the galvanometer as shown in the figure. Our aim is to find the value of Ig. So, it is given that the current flowing through the circuit I is equal to 2 ampere. So, first we take the junction P and we apply our Kirchhoff's first law. So, at junction P, I is equal to I1 plus I2. I is divided into 2 current, which is I1 plus I2. From this equation, we get an expression for I2 as I minus I1. This I am keeping it as first equation. Applying Kirchhoff's second law to the junction PQSP, that is the first triangle, small triangle I have taken, and here I am applying Kirchhoff's second law. So when you apply 5I1 plus 10Ig minus 15I2 is equal to 0. Here instead of I2 you have to substitute the equation 1, which is I minus I1. So when you substitute and when you simplify, it is a normal simplification. When you simplify, you get the equation as 20I1 plus 10Ig is equal to 15I. Here we are substituting the value of I, which is given as 2 ampere. So when you substitute instead of I2, you have 15 into 2, which is 30. So 20I1 plus 10Ig is equal to 30. You can simplify this equation by dividing by 10 throughout the above equation. So we get 2I1 plus Ig is equal to 3. Have this equation as equation 2. Next for the loop QRSQ, we are applying Kirchhoff's second law. So when you apply Kirchhoff's second law, we get 10 into I1 minus Ig minus 20 into I minus I1 minus Ig minus 10Ig is equal to 0. Now, with a few steps of simplification, we get the expression as 30I1 minus 40Ig is equal to 20I. Now, the whole equation, if you divide it by 10, you will have 3I1 minus 4Ig is equal to 2I. We know the value of I as 2 ampere. So, when you multiply that by 2, we get the equation, third equation as 3I1 minus 4Ig is equal to 4. So, equation 2 we are multiplying by 3 and equation 3 we are multiplying by 2 in order to get the value of Ig. Just how you solve a normal algebraic equations you have to solve. So you get 6I1 plus 3Ig is equal to 9. 6I1 minus 8Ig is equal to 8. Subtracting the above two equations, you get the answer as 11Ig is equal to 1. Hence Ig is equal to 1 by 11 ampere. The next problem. Two cells each of 5 volt are connected in series across the 8 ohm resistor and 3 parallel resistors of value 4, 6 and 12 ohm. Draw a circuit diagram for the above arrangement. Calculate the current drawn from the cell and current through each resistor. So first the circuit diagram is drawn. We have got two cells of voltage V1 and V2. And our resistance R1 is connected across series. After you have got 3 parallel resistors, that is 4 ohm, 6 ohm and 12 ohm, that is R2, R3 and R4. 3 are connected in parallel across each other. That combination is connected in series with R1 and just see how the connection is done. Now we have to find the current and the current through the each resistor. First, let us find the effective resistance of the circuit. Since R2, R3, R4 are connected in parallel combination, we use the formula 1 by Rp is equal to 1 by R1 plus 1 by R2 plus 1 by R4. So, substituting the values, taking LCM and simplifying, we get the value as 6 by 12, which is equal to 1 by 2. That is 1 by Rp is equal to 1 by 2. So, Rp will be equal to, that is resistance across the parallel connection will be equal to 2 ohm. Now, resistance R1 and Rp are connected in series. So, the effective resistance Rs is equal to R1 plus Rp, which is equal to 8 plus 2, which is equal to 10 ohm. The total voltage is V is equal to V1 plus V2. Both are connected with the same potential. So, it is 10 volt. Next, current through the circuit I is equal to V by Rs. V voltage is 10 and Rs is 10. So, the current through the circuit will be 1 ampere. Next, potential across the parallel combination will be V dash is equal to I into Rp. I is 1 and Rp is 2 ohms. So, the voltage will be 2 volts. Next, we have to find the current in 4 ohm resistor. So, I will be equal to V dash by R2, which is equal to 2 by 4, which is equal to 0.5 ampere. Similarly, current in 6 ohm resistor, I is equal to V dash divided by R3. Since it is across a 6 ohm resistor, the R value should be substituted as 6. Similarly, when it is current across 12 ohm resistor, the R value has to be substituted as 12. So, substituting, we will get the values as I is equal to 0.17 ampere. The next problem. In a potentiometer arrangement, a cell of EMF 1.25 volt gives a balancing point at 35 cm length of the wire. If the cell is replaced by another cell and the balance point shifts to 63 cm, what is the EMF of second cell? So here we use our potentiometer balancing formula as E1 by E2 is equal to L1 by L2. Here it is given as epsilon 1 divided by epsilon 2, where epsilon 1 and epsilon 2 are the EMF of the two cells. So this is a very simple formula, and substituting the values of epsilon 1 and L1 and L2 and simplifying, we get the answer as 12.5 into 1.8, which is equal to 2.25 volt. The value of EMF of the second cell is found to be 2.25 volt.